There are certain rules about the interior angles of polygons that apply to all sorts of different kinds of polygons. So we're going to start off looking at a triangle and trying to see if we can figure out what is special about the interior angles of a polygon. So the first thing I'm going to do is I'm going to measure these angles. I need to measure angle L, angle M, and angle N. So I'm going to start with N. I'm going to line my protractor up right here. And when I line that up, I see that angle N is 110 degrees. So what I'm going to do is next to angle N, I'm going to put that measurement in place. I'm going to measure angle M now. Slide my protractor over here. This one looks like it's going backwards, but that's okay. And what I see is it starts at 0 right here, and I go up, and angle M measures 40 degrees. So now I just need to measure angle L. This one's going to be a little trickier because I'm going to have to rotate my protractor a little bit. It might take me a minute to line it up. Got to get it right through the 0 degrees here, and I notice it looks like it's somewhere either 30 degrees or 150 degrees. But because I know this is an acute angle, I know that it's 30 degrees, and so I'm going to put that here. So now what I want to look at is angle L, which is 30 degrees, plus angle M, which is 40 degrees, plus angle N, which is 110 degrees. If I add all these degrees up, I get the total number of degrees inside this triangle is 180 degrees. And that is actually a rule. Every triangle, no matter what it looks like, whether it's obtuse or acute or right or scalene or equilateral or isosceles, if you take its angles and you measure the angles and add them all up, it will always equal 180 degrees. I'm going to show you another example with this equilateral triangle here. If you notice, I have these dotted lines right here. Imagine that I cut this angle off, okay, and I'm just going to line it up here. And now I'm going to do the same thing for this corner right here. I'm going to cut off right along this line, and I've got this angle, okay? And the last thing I'm going to do is I'm going to cut right here at the top where C is, and I'm going to cut that off. Now, if I wanted to line this up with my others, I'm going to have to kind of flip it around a little bit. And look what happens. If I put that angle right inside here, okay, these three angles create a straight line. So these three angles together are like supplementary angles. If we add them all up, they equal 180 degrees. So like I said, it doesn't matter what kind of triangle you have. The three angles together will always equal 180 degrees. And that's important because we can use that information to help us find missing angle measurements. Okay? If we look at this triangle, we know that this angle here is 34 degrees. This angle up on the top is 23 degrees, but we don't know this angle right here. We can tell that it's an obtuse angle, but other than that, we don't know anything. So if I want to find this missing measurement, what I'm going to have to do is I'm going to have to take the two angles that I know, 34 degrees and 23 degrees, and I'm going to add those two together. And when I add those together, I see that I get 57 degrees. So this and this together equals 57 degrees. Now, if I want to find this missing measurement, I know that all triangles will add up to 180 degrees. So what I'm going to do is I'm going to take this 57 degrees and I'm going to subtract it from 180. And when I do that, I'm going to get, oops, sorry about that, that makes no sense. When I do that, I'm going to see that I get 123 degrees. So that means that this missing angle right here is 123 degrees. Let's try one more. If I look at this triangle here, I see that this angle is 51 degrees, and I see that this angle here is 73 degrees. So together, those two angles make up 124 degrees. Now, if I want to find this missing angle down here, what I need to do is I need to start with my 180 degrees, and I'm going to subtract my 124 degrees. So I'm going to need to do some regrouping here, and I see that this angle is 56 degrees. Now, knowing that the angles in a triangle always add up to 180 can help us with these other measurements as well. Okay? What we can do is we can take other polygons and we can figure out how many degrees are inside these other polygons by breaking them into triangles. Let me show you. For example, if I were to take this rectangle and I were to split it like this into two triangles, I would know that each of these triangles was 180 degrees. So if I wanted to know in this quadrilateral how many degrees I had, what I would do is I would say, okay, well there's 180 degrees in each triangle. I broke my shape into two triangles, which means that this quadrilateral has 360 degrees. And that's true for every quadrilateral. Let me show you. I'm going to take this quadrilateral over here, and I'm going to break it into triangles. So I start at one vertex. The way you break it into triangles is you start at a vertex, and you go from vertex to vertex. Now you can't cross lines. I can't do something like that, okay, because now I have measurements in here in the middle, and we don't want those. All we want are the outside angles, okay? So if I were to go from this vertex to here, that's not going to be a triangle. So I've got one here, and if I go here, again, that doesn't create a triangle. So once I have this broken down, I see that there are only two triangles, each triangle 180 degrees, which means this quadrilateral is 180 degrees times 2, which means it's 360 degrees. Now, we've got other types of shapes. We've got hexagons, we've got pentagons, we've got octagons. This will work for any type of polygon. It even works if the polygons are not regular polygons, okay? So here's what we're going to do. Let's break this in half. I'm going to start up here at the top. I can't go from here to here, but I can go to this vertex, and I can go to this vertex. So what I've done is I've broken this pentagon into three triangles. So what I have for my interior angles is 180 degrees times 3, which means a pentagon, if you add up its interior angles, will add up to 540 degrees. One more shape we want to look at. Let's look at our hexagon. All right, I'm going to break this into triangles. I've got one triangle here, one triangle there, and one triangle there. Remember, we can't overlap our triangles. So we've got 1, 2, 3, 4, which means for a hexagon, 180 degrees times 4 means that all the angles inside the hexagon would add up to 720 degrees. Now I'm going to show you how we can use this information to solve problems. And what we're going to be doing is we're going to look at a quadrilateral. So if I look at this quadrilateral, and I think, how many triangles can I break this into? I would break this quadrilateral into two triangles. So I know that this is 180. Oops, sorry about that. I know this is 180, and I know this is 180. So together, this whole quadrilateral would add up to 360 degrees. So I know the whole thing eventually has to add up to 360. What I want to find is this missing measurement right here. I know that I have three measurements already listed. I have 50 degrees, I have 65 degrees, and I have 140 degrees. So I'm going to start this problem just like I did my triangle problems, where I'm going to add everything together. And when I add all this together, I see that I already have 255 degrees in this quadrilateral. Okay? But it's not going to add up to 180 because it's a quadrilateral instead of a triangle. So what I need to do is take this 255 degrees and now subtract it from my 360. So 360 minus 255, oops, sorry about that, gives me 105 degrees. So I know that this missing angle up here is 105 degrees.